Okay, so if you are following along in your notes, it probably says Unit 10 at the top. This is an old Unit 10. We're actually referring to this as Unit 8c. So it will have a quiz that accompanies this, which we have scheduled, I think, for this Friday. So if you take a look, we're going to talk about sum and difference of cosine and secant and sine and a whole bunch of stuff. It's all formula related, right? So the first thing we want to talk about is why we're doing this. So an example of where these formulas are going to come from is that we're going to deal with radian values that are within the unit circle, but not the ones that you memorize as part of the unit circle. So if you take a look, pi over 12 is an example of a non-unit circle value, traditional unit circle value. So what we're going to do is we are going to use fractions to add or subtract unit circle values in order to come up with pi over 12. So let's talk about denominator of 12. So if I have a denominator of 12, as such, I know that whatever I have with here and here has to give me 1/12, meaning 1 pi over 12. I can add or I can subtract. So what about something like 4 and 3? Does that make sense? And when I reduce each of those fractions, I end up with what? 1/3 minus 1/4. Those are both unit circle values, pi over 3, pi over 4. Yes? Which then I can reduce here and here. So this would be, pi over 3. And this is pi over 4 equals pi over 12. So these are both unit circle values with a denominator of 12. Right? That's the first skill that you need to be able to have in order to do the problems in this unit, adding and subtracting. Okay, so what we did here is, I'm going to erase all this. We're going to talk about, there's a list of them written as denominators of 12. Most of you will be able to pick this up very quickly just because of what we've been doing with reducing by hand. Okay, pi over 4 minus pi over 6 also does the job. Pi over 4 is 3 pi over 12 minus 2 pi over 12 is also 1 pi over 12. So, if you look at the very first example in your notes, you are going to be asked to tell me what is the cosine of pi over 12 without a calculator. Step 1 to doing that is to rewriting pi over 12 as the either sum or difference, adding and subtracting, of two unit circle values. Okay. From here to here. Does anyone have questions about that self-generation of the adding or subtraction statement? So, given problem, you have to do this first. Okay? In order to come up with these, you need to rewrite them as a fraction of 12, and then you'll end up reducing them back to unit circle values. Now, there are 3 formulas in this unit, this section. The 3 formulas will be given to you. You can have them out, you can have your notes out, you can rewrite them, whatever that you need, but please be careful if you rewrite them that you get the signs in the correct order because the signs really matter. So if I look at the formula, U and V are just placeholders, meaning the first and the second angle that you wrote down. Alphabetically, U comes before V. Pi over 4 is before pi over 6 within the parentheses. If I look at the formula on the right, I'm going to take the cosine of whatever the first value is, multiply it by the cosine of the second, and since I am subtracting, I can go all the way up top and say, okay, look, I'm dealing with all bottom signs. So I'm going to use the 2 purple signs from the formula. I'm not going to use that plus sign I didn't highlight or the minus at the end. You stay in line with your signs. So one strategy for doing this is take your original problem, rewrite it in adding and subtracting form, and then identify what is U and V, then rewrite using the formula where I just plug in what U and V actually are. So you could go from here right to here, then pull out the unit circle in your brain and substitute. So what is the cosine at pi over 4? What is the x value at pi over 4? Root 2 over 2. The cosine at pi over 6 is root 3 over 2. The sign at pi over 4 is root 2 over 2. The sign at pi over 6 is 1/2. I kept my plus sign here. So it's a product plus a product. This is the work that we generate from our knowledge of the unit circle. Then we let go of that, and our last step is to do the adding of the fractions. First product, second product, final answer. For those of you that did not like the last 2 units, hopefully you like this one because this is concrete numbers. We're back to actual just plugging in things, using formulas, and manipulation, fraction reduction, and algebra. Very straightforward. Any questions? All right, second example, secant of 7 pi over 12. Okay, we have a problem, minor problem. Secant is not one of the 3 formulas that you have. You have a cosine formula, you have a sine formula, and you have a tangent formula. Push this up just a little. Okay, you do not have a secant formula. So we have to go back to 2 units ago when we defined somewhere that cosine of x is equal to 1 over secant x. We didn't use it very often, but we did say that secant x is 1 over cosine x. Do you remember that? So I'm going to use this definition and say, okay, I want to add 2 fractions that add up to 7 pi over 12. But I'm going to use my cosine formula with a plus sign instead of secant. I'm going to go to 1 over cosine using this. So if I follow, and you have this in your notes, follow the signs across. If cosine is a positive, then as I come across on the other side in the middle, I should have a minus sign here. So my direct formula, I'm going to erase this here for a second, is this is the product minus this product here, all of which is set into a fraction denominator with 1 in the numerator. All right, let's take a pause. Given the formula, are you okay getting to here? If I give you the formula.
Yeah.
Okay, so that's the new stuff, I feel like. Now we're just doing a bunch of nuts and bolts and, inventory of the unit circle. Do you know what cosine of pi over 4 is, cosine of pi over 3? Can you think all that out?
Yeah.
All right, for the sake of time, I'm just going to pop it up here. All right. The cosine of pi over 4 is root 2, all this. I'm rewriting exactly what's here using the actual numbers. Again, we have this product minus a product. Which then leads us to a simplified answer that looks like this. Please be careful. Sometimes you get so into the numbers, you forget that you actually have this complex fraction within a denominator. Sad to say, we are not done here. What is the rule when I take a number? Like if I would have 1 over 2/3. What do I multiply 1 by? The reciprocal, correct? Same thing is true here. I'm going to take 1 and I'm going to multiply by the reciprocal. So I'm taking the bottom and flipping it over. When I do that, I get this. And now I have a new problem. Now I have to rationalize, correct? Because I can't have roots in the denominator. How do you rationalize when you have the subtraction of two roots? You are absolutely right. How do I get rid of 2 minus root 6? Yes, we're going to use the conjugate. Yeah, yes, conjugate. So I'm going to multiply top and bottom by 2 plus root 6. 2 plus root 6. Right, so I've got this times this, this, and this. Please remember, the top is distributive property. 4 times this, 4 times that. The bottom is a FOIL. When you FOIL, you'll end up getting this. Can you tell me how the final answer ended up the way that it did? That's our final. Negative root 2 minus root 6. The 4 is canceled, distribute the negative, right? Yeah. So we still have to reduce. Now, just as an aha moment, take a look at what you are actually doing in math class right now. From the beginning of the year until now, this really is everything. You've come so far. But just in general, like, look at the math of this, is what I'm trying to get you to see. Like, this is rationalizing. This is complex fractions. This is unit circle. This is all of that. This is these awful fractions that on the prerequisite, most of you are like, do what? You want me to flip what? Yes. Okay, so this is where we've been going all along. This is the kind of algebra skills and unit circle use that you will need for calculus. Okay, right now it's very formula-like, but that's okay. Okay, so moving on. Example 3. Example 3 isn't any harder than what we've done before. I actually prefer these types of problems, maybe you will as well, because they are not unit circle values. They're all right triangles in the coordinate plane. So if I read this, I mean, it looks very, very difficult, right? Like, look at this. It's alpha plus beta, cosine, and I have to be at these intervals. But the intervals are just telling you the quadrants. They could have just cleaned it up and said, look, draw me a triangle in quadrant 1. Right? Draw me the reference triangle in quadrant 1. The A over H values are this over that. So what I mean by that is that given this is what I'm finding, this will be the formula that I use. Right? You have the formula at the top. I'm adding, so I follow my signs across, gives me a minus here. I then set up a reference triangle in quadrant 1. Well, why did you know to put it there, Mrs. Gomer? Okay, Mrs. Gomer will answer. Because right here, 0 to pi over 2 means quadrant 1. We've done these before. Cosine adjacent over hypotenuse. In my second triangle, I'm going to draw this in quadrant 3. My sine, which is opposite over hypotenuse, is there. And the tricky part here is, don't I need to have the cosines and sines of both of these? So I have to use Pythagorean theorem to complete the triangles. Right? So we're here. A lot of times they like special right triangles for these because they're not trying to trip you up on, you know, the roots and whatnot. So what would you tell me is the length of the opposite side? 5 what? 13. That's a special right triangle. 5 what? 13. I failed you. 5 blank 13. It's got to be less than 13. What's that number? Special. No. 12. 5, 12, 13. That is a special right triangle. You never knew that? It's always a combination. So 10, 24, 26. Special right triangle. What about 3 blank 5? 4? Okay. Why did I make this one negative, but I didn't make the 12 negative? because I went to the left. Okay. So we knew in the first one that the cosine of alpha was equal to 5/13, and now we know the sine of alpha is equal to 12/13. And we knew from the second given information that the sine of beta was equal to -3/5, and now we know the cosine is -4/5. Don't we need these four numbers just to go right into my formula then? Yes. So if I go to the next screen, I can plug all of that in. And then you're back to fractions are your friends. Fraction times fraction minus fraction times fraction. Real quickly, do you need me to go back to the triangles? Anyone? We're okay? So if I were to describe this lesson, I would say it's annoying and it's tedious. But I don't think it's hard. It's just a new way of applying a new formula. Not really, it's new for you. It's not like new in the world. We didn't discover it. Okay. First fraction multiplied gives me the -20/65 minus, this minus is the same, and then up here, -36/65. Okay, I would like you to try example 4. If you want to change this to an X instead of a beta, that's fine if the Greek letters goof you up. Both of these will involve you drawing a right triangle, finding cosine. We're going to draw it over here. This is what we would consider a hybrid problem. It involves unit circle values. You don't need a triangle for pi/6. But you will need a triangle to find beta because it's not a unit circle value. So here I've applied the formula for you, substituted in based on the given information. I want you to try. If you have questions, I'll just walk through the rows. Let me know. that's what gets plugged back into the formula, and it'll look like this. Cosine U, cosine V, plus sine U, sine V. It's a substitution of exactly what you were given, then you can replace those further. Did you get that? Answers at the bottom. Negative 4 root 3 plus 3 over 10. I'll give you more of the work then, and just for those of you that are at the end. Here are my fractions.